Alright, this is a pre-lab lecture for Lab 6 in which you are going to explore an NMOS inverter and an NMOS amplifier. Turns out the circuit for both of these is really identical. So here's the simple circuit you're going to be building. There's an N-channel MOSFET, and you have a resistor R1, which is going to be 500 ohms, and you're going to tie this up to a 10-volt supply. And the drain of the MOSFET right here is going to be the output. So that's going to be V out, and it's going to be measured with reference to ground. And the input is going to be the gate voltage, and so the input will actually be VGS, the gate to source voltage, and we can also call that V in. Now this circuit can be used both as a logic inverter, so it can be a crude, this is not a high performing one, but it would have the basics of a logic inverter, where if this input is A, or let's say we'll call it V in and V out, okay, VO. If we made a transfer characteristic of this, V in and VO, all right, and we could put our little limits there of VO high and VO low, and let's put some VI low and VI high. Okay, we'll find that this actually has some kind of a characteristic that looks, very much like an inverter. So when the input is below some threshold, the output will be high, and when the input is above some threshold, the output will be low. And the actual values of the static discipline defined by VO high, VO low, VI high is going to be determined. You'll be able to determine it from the parameters of the circuit. Now you don't know how to do that yet, but by the end of the lab you should be able to determine those four parameters. So we can use the circuit as a logic inverter. All right. We can also use it as an amplifier, and it looks very much the same, the symbol-wise. We'll have some V in, have some VO, and of course this is a reference to ground. Okay, it'll be the same for up here. And now we will claim that if you put in some voltage, let's do it this way. If I put in some V in, all right, that has some DC value and a small AC, then I'm going to claim that the output will be some DC voltage with a larger sinusoid. Okay, so here I'm plotting something versus time. Okay, note this right here is a DC transfer characteristic. So I'm not plotting anything versus time here. I'm plotting output versus an input. In the second case, I'm plotting the input versus time and the output versus time. Now I could also plot the output versus the input. Okay, and what I would find is that in some region here, I actually have some slope. Call it A. Okay, it is the same A that's here. In other words, if we put in a small signal, let me redraw this amplifier. If I put in some small signal, I'm going to put a little squiggly now. Let's say that's 10 millivolts sine omega t. All right, going in. Then the output is going to be some voltage gain A times V in, small signal. Okay, where A is going to have some magnitude that's greater than 1. If it does, then it's actually amplification. And we'll find out this number is fairly large. And really what we're doing here is we're using the same circuit as we used for the inverter. So if I draw the transfer characteristic here, and you'd have something that looks like this, okay? And actually it's going to kind of curve down. We'll see that it'll curve down and then kind of bottom out like this. If you operate at some point, remember we've talked about operating points when we did diodes, so if you have some operating point VO and some operating point VN, all capital, then if you operate around that point, there's a slope. And if you put in some small input, okay, what you'll get is you'll get some larger output. Okay? And that's what you're going to explore in this lab. So we've already talked in class about one model for the MOSFET. You're going to need to have a model for the MOSFET in order to study these circuits. So let's cover that, MOSFET models. All right, so there's several models. One would be the ideal switch model. And all that is literally a switch. So this is drain, this is source. The source is down here. And then there's a controlling voltage, the gate. And the voltage between gate and source is VGS. And this switch is closed when VGS is greater than some threshold voltage, and it's open when VGS is less than some threshold voltage. Okay? So if we were plotting, for instance, the resistance of this switch, all right, and I'll call it RDS because it's the resistance from the drain to source. If I was to plot that between as a function of VGS, then, and here's VTH, then what we would have is, it would look like this, where this would be infinite resistance and this would be zero resistance, right? And as the input crosses that threshold of VTH, the switch goes from being open to being closed. So that's the ideal switch model. Now we'll call that the S model. Okay, then we can augment that to what we call the SR model. Because in reality, when the switch is on, it's not a dead short. There's some on resistance. So now we'll have a model that includes an ideal switch, but then has some resistance to it. Okay, RDS on is what we'll call that. Here's the source. Here's our gate. Okay, again we have VGS that controls it, and still have the same control law. When VGS is greater than some threshold voltage, the switch is closed, and it's open when VGS is less than some threshold. Okay, so we went over all of that in class, and that's all good for looking at least the principle of operation of a logic inverter. Okay, but it will never predict these cannot predict the transition region of the logic inverter, or the inverter for that matter. Okay, what do I mean? So when you have your transition, or your output characteristic, DC transfer characteristic, okay, SR model, the SR model can kind of capture maybe both of these. Okay, SR model. It can tell you if, for instance, Vn is greater than some amount, eventually here, this voltage, we looked at this in class, is simply going to be the RDS on over RDS on plus, what do we call it, R1 times 10 volts. Okay, you can just use the RS model for that. But right here, you cannot model, this transition cannot be modeled or cannot be predicted by the SR model. The SR model would say that you are actually up at some VO high level all the way up until you hit your threshold, and then you go straight down, right? And this value here would be the threshold voltage, and that's not how the transistor actually works. So if you're trying to understand what's going on in that transition region, then you need yet another model. And that transition region is actually where we're going to use this inverter circuit as an amplifier in our second application here, as amplifier. Right here, amplifier, inverter. Okay, so we have to augment our model. So here's the third model that we'll use, and it's called the voltage-controlled current source model. Actually, I think they give it the name, what do they call it in the book? Remember, maybe they call it the CS model, controlled source. I'm not sure. Okay. Regardless of the name, here's how you model the transistor using a controlled source. Instead of having a switch with a resistor, you put in a current. I'll call it a sink. It's a current source, but I call it a sink. Sorry, I had an interruption there, so I can't remember what I was saying. So let me start over again. We have a controlled current source that we're going to connect between the drain and source instead of our switch and resistor. Okay, we still have our controlling signal from the gate. It doesn't really go anywhere. That's one of the things about the MOSFET, is that the current, there's no current that flows into the gate. Never any current that flows in the gate, so it's always equal to 0. But the voltage is important. The voltage is what controls it. So we have VGS here. And here's the dependency. The current flowing from drain to source is dependent on the voltage according to this expression. A constant K divided by 2 times the gate to source voltage, VGS, minus the threshold voltage, and the whole quantity is squared. And this is valid for VGS greater than or equal to V threshold. And if it's going to be 0 if VGS is less than V threshold. Okay? So if VGS goes negative, it's not like this current turns around and goes the opposite way. It's just off. There's no current. And of course, no current is an open switch. So this model is, in a sense, it mimics the switch model when the switch is open circuited, when it's open, but when the switch is, quote, on, in this case we don't have a short, we have a current source. Okay? Now there's another constraint on when the transistor operates in this mode. Okay? And the thing is, this will become clear later as we work with MOSFETs here over the next week or two. But this model represents the transistor actually operates in several different operating modes, kind of like the diode, where the diode could be on and the diode could be off. The transistor actually has 3 regions. It has a region. So let me write that. Transistor has 3 operating regions. Okay, one is cutoff. That's when VGS is less than the threshold voltage and IDS, then the current is 0. It's like an open switch. Okay. The second mode we would say is it's called the Triode Region, and I haven't described that yet. But for now, this could be modeled with several models. Currently, okay, so I'd just say simplest model of this is when the switch is on and we have RDS on. Okay, switch on. Here's our drain, or our source and our drain, if you will. Doesn't matter. Okay, simplest model would be that. There's another model that is, I'll just say TBD. We'll describe that later. We actually don't need to use that one today. The main thing is that it's called the Triode Region, and then the third is called the Saturation Region. And this is where the transistor behaves as a current source, behaves as a controlled current source. And there are conditions for that. What are the conditions? The saturation region, and this is where we have IDS is equal to this constant K over 2 times VGS minus V threshold quantity squared. And that's for VGS greater than or equal to VTH. The condition is that, let's see, the drain to source voltage must be greater than VGS minus the threshold voltage. Or another way of writing that is we can say that the gate to drain voltage must be less than, let's see, make sure I write this right, threshold. Okay, or, sorry, I'm searching for the best way to write this. Or we can write this as V drain, because VGD is V gate minus V drain. So we could write V drain must be greater than V gate minus V threshold. This is the one that I actually like using the most. So with this model comes the requirement that V drain must be greater than VG minus V threshold. Okay, so let's look at an example here. Let's suppose we have our 5-volt source. We have R1, and here we have our MOSFET. And let's say that the gate to source voltage is set to 2.5 volts. Okay, and suppose that for this transistor we'll call it M1. So sometimes we use M as the reference designator for MOSFET. It's like R for resistor. Let's suppose that V threshold is equal to 2 volts, okay? And we have yet to determine what K is, but we don't need that for the moment. So the question is, this is V out equal to V drain equal to V drain to source, because the source is grounded. The question is, for what range of V out or V drain is the transistor in saturation mode? Okay, well, it's going to be, if we go back and look at our rule, it is that the drain voltage must be greater than the gate voltage minus the threshold. VG is at 2.5 volts, and the threshold voltage is at 2 volts. So that's equal to 0.5 volts. Okay, so as long as VD is greater than 0.5 volts, the transistor is in excuse me, saturation mode. What does this mean? Okay, so if it's in saturation mode, we can model it as a controlled current source, which means that we can replace the transistor with a controlled current source. Okay, here's V out, and this is going to be K over 2 V. If we have the input V in connected to the gate, then it's going to be VGS, but we'll say V in minus V threshold squared. Okay. Now, what if I detach this transistor and out of this circuit for just a moment, just to show you how this transistor is behaving? Let's say I set this voltage to 2.5 voltage, the gate voltage. All right, the source is grounded, and I take hold of the drain. And what I do is I connect, say, a battery to this drain, and it's a variable battery, V bat. Okay, and I look at the current that is flowing into the drain of this transistor. Okay, according to the model, I have a controlled current source, and this source has a value of K over 2 V in minus V threshold quantity squared, and it is not a function of V bat. So if I were to plot I drain versus V bat, okay, then as long, let's draw a line here, at VG minus V threshold, okay, which is equal to 0.5. As long as I'm above that, I have a constant current, and that current value is going to be whatever K over 2 V in minus V threshold squared, whatever that evaluates to. Now once, and in this region, from here on up, I'm in the saturation mode. Saturation region. Okay, mode, sorry. Now once I go below 0.5 volts, now I'm no longer in the saturation region, and I haven't described what that looks like. I'll just put in a kind of a dotted curve, but this region here is actually called the Triode Region, and we're not going to explore that right now. Okay, so what have we learned here? If the transistor is in its saturation mode, the transistor acts like a current sink, and it doesn't matter how much voltage you put between the drain and the source, it still will suck, if you will, or draw the same amount of current, and that current that it draws is going to be programmed by the gate to source voltage. So we really have like this programmable current sink. Okay, so let's consider now, if we go back up to this circuit here, and let's write an equation. I'm going to call this VDD, and I'll call this R1, I guess. Let's express VO. Okay, let's express VO. Well, okay, I can do KVL, and I can see clearly that the current flowing through R1 is whatever the current source will program, the current sink will program. through it, and the VO is simply VDD minus the voltage drop across that resistor. So it'll be VDD minus R1 times whatever ID is. Okay? And ID is going to be equal to this expression of K over 2 Vn minus V threshold squared. All right? And this is valid for Vn greater than or equal to V threshold and V out, or V drain, we said greater than VG, right? VG, which is going to be the Vn voltage, minus the V threshold. All right, this is Vn minus V threshold. All right, so these are, keep that in mind here. All right, so now let's plot this. What does this look like? If we put Vn on the horizontal and we put Vo on the vertical, let me put a vertical line here at V threshold. Okay, so since this equation is valid only for Vn greater than or equal to V threshold, let's evaluate it right at V threshold. So at V threshold, what do we have? We have Vo is equal to VDD minus R1 times 0. And it's 0 because the current is proportional to Vn minus V threshold, and Vn is V threshold, so that difference is 0. Okay, so Vo is equal to VDD. So right here I've got VDD, which I guess in my case I drew as 5 volts. You're going to do it for 10 volts. Right? Now from then on, what I actually have is the form. Okay, so form of Vo is some constant A0 plus, so if you expand the Vn minus V threshold, we'll get some constant V1 times Vn, and then we'll get some constant A2 times Vn squared. Right? So this is a square law, and we can see that it is the net effect, the net result is that the voltage is dropping from VDD, and it's going to grow according to square law. So it'll be like, if we went both ways, it would go like this. But of course, that doesn't happen over here. So we're going to be at VDD for all voltages less than V threshold because the transistor is actually in cutoff region there. And then it's going to accelerate according to this expression here. Right? It's going to take a dive. But then at some voltage here, we're going to have some point where Vd is going to fall below the gate voltage minus the threshold voltage, and it will no longer be in the saturation region. We're not going to try to model that now, but I'll just show it as basically this thing will not, it's not going to continue going negative like this. It'll curve out, take a swing, and asymptotically go to 0. And this middle region is the saturation region. And up here is what we call the triode region. All right, and remember, what I'm drawing here is the DC transfer characteristic of the inverter. All right, and so with what you have so far, if you knew the parameters of the MOSFET, the K and the V threshold, you could predict all of this. You could predict things in the cutoff and in the saturation region. You wouldn't be able to describe the triode region at this point, but at least the saturation region, and most importantly, saturation region. Okay, so I don't want to make this this pre-lab too long, but I wanted to give you the basic modeling for the MOSFET, and then the last thing I want to do now is to point out how you can use this as an amplifier. So let me just redraw this, and okay, as this takes a dive, if we were to position ourselves at some operating point right on this transition curve, and we'll call it, it's at capital Vn and capital V, capital O. All right. If you then put in a small perturbation around there, small perturbing input signal, the output that results, the small output, will be the input, small signal input, times the slope of that curve at that operating point. Okay. So using the saturation expression, okay, that is this guy here, okay, determine the slope. Determine the slope. Just do that by taking the derivative. All right, so we're going to look at dVO dVn. And you'll find that we've got a minus 2 times R1 K over 2 quantity Vn minus V threshold to the first, and then times the derivative of Vn, which is 1. And then this is going to be evaluated at Vn equal to our capital Vn. All right, that is the slope. Okay, that is the slope of our curve there. So we really have minus R1 times K. So once again, we can write, to summarize here, we have VO, and I'll put a little small signal now. VO is going to be equal to minus R1 times K, 2 times K over 2, times Vn, the capital Vn, minus V threshold. That whole thing times little Vn. Right? This is our small signal voltage gain. Small signal voltage gain. Okay? And we can also, this can be rewritten, can be expressed in terms, of, let's see, you could express it in terms of IDS, the drain current, the operating drain current, or we could write it in terms of capital VO. And I'm not going to do that here, but I'll let you work on that. But this at least gives you an expression for the small signal gain. So for instance, as an example, to close this off, if V threshold was 1.5 volts, and let's say that K, we look at K for a moment. Actually, let me write the saturation expression again. It's going to be IDS is equal to K over 2 VGS minus V threshold quantity squared. So we've got to get amps out of K times volts squared. Right? So K has units of amps per volt squared. So let's say it was 0.04 amps per volt squared. Okay? Now if Vn, capital V, capital N, was equal to 2 volts, okay, then A, the voltage gain, would be equal to minus, and let's say that R1 was equal to 1 kilo ohm in this case, right? So we'd have minus 1,000 ohms times 0.04 amps per volt squared, that's K, times 2 volts minus 1.5 volts. So that would give us minus 40 times 0.5, right? Or minus 20 volts per volt. Okay? So that means if you put in a 3 millivolt sine omega t going in at your gate, okay? I'm not drawing the whole circuit very well, but this is, okay, if you put this at the input between the gate and the source, and this was tied up to whatever we had it to, 5 volts, and this is 1K, then the voltage you would have coming out, small signal wise, this is input small signal, the small signal portion that would come out would be equal to minus 60 millivolts sine omega t. All right, so you have amplification. You put in something small, and we would get something that would be 20 times larger. And the key to figuring out what is the amplification is simply going back to that DC transfer characteristic, and in that middle transition region, figuring out what is the slope at the operating point of your amplifier. Okay, so I think I'll stop there. That gives you the theory that you need, I think, to tackle the lab. And we'll pick it up from here in class on Wednesday.